All right, hello, my fellow EM aficionados. So, um, been turning out the videos kind of quickly recently, but had a little bit of a lull there. But I have been working on a couple, and this one in particular, I have been wanting to do for a really long time, just as like a concept video, um, because this is a neat one to address some kind of fundamental concepts related to electron microscopy. And so this question is, do I need to worry about charging when performing STEM? Okay, STEM again meaning scanning slash transmission electron microscopy. Okay, which refers to either scanning transmission electron microscopy or transmission electron microscopy. Okay, so we're going to answer this question today and hopefully put this to bed. But before we get into the slides, the thing I want to start with is if you have a proper fundamental understanding of how STEM works at its most basic fundamental level, like if you can just kind of distill it down into its essence, this is a question that you should be able to answer on your own. Okay. So if you want to do that, maybe what you can do is like pause the video and then, answer the question, and then you can follow along and see, see what if you're consistent here. But anyways, that's one of the things I want to, tell everybody is this is something that most people can just logically work through and figure out. Again, as long as you fundamentally understand how STEM works. Okay. So now that we have that out of the way, okay, so when we're talking about charging, so charging is literally when you have an accumulation of charges inside of your material. Okay, so those can be negative charges, those can be positive charges. So this is a schematic of the charging process. So we have a sample that is an insulator, which is not grounded, and it is basically, sorry, it's this thickness arrow should have auto-populated, okay? But this is infinitely thick, right? From the surface into the bulk, okay? So when I shoot my beam of electrons at the sample, there's a few things that can happen, right? So my electrons can be backscattered, right? So they can actually leave the sample, okay? And I can also have the case where my electron goes into the sample, but I also generate what are called secondary electrons from within the sample that also get ejected, okay? So depending on the dynamics of these two processes here, you're going to end up with some kind of charge distribution in your specimen, okay? So in the case that we see here with like an insulator, we're going to end up with potentially some, a net positive at the surface, right? Because we're ejecting all these secondary electrons, which tend to come from the surface. So we're going to end up with a net positive charge there. But then in the bulk, we may end up with the reverse, right? Which is, a negative charge distribution, right? Because not all of those electrons that I shoot in, right, actually make it out, right, or are backscattered. Many of them aren't, again, depending on the material, and those will then sit inside of the sample, especially, again, if we don't have any path to ground, okay? Again, we're assuming an insulator, and we're also assuming no grounding, and the sample is infinitely thick, okay? So these two yields, eta and delta, right? This is the backscattered yield and the secondary electron yield, okay? So those two parameters are actually very important when we're considering the charging process, because basically if the yield combined of those two terms is equal to 1, then we can't have any charging, okay? Because basically for every electron we're putting in, we're getting 1 out. Okay, so if that's the case, then by math, right, we can't be having charging. Okay, So you can see this schematically in this plot here, which plots the yield as a function of electron voltage, right? And again, we're assuming a semi-infinite, semi-infinitely thick sample that is not grounded, okay? So we can have a net negative charge up to some voltage, at which point the yield goes to 1, and then at that point, my net charge becomes positive. The yield reaches a maximum, and then it starts to come back down again, and then there's another voltage where we hit a yield of 1 again. So there's really 2 voltages here where we can avoid charging. Okay. And then if we keep going beyond that, we start to get an accumulation of negative charge. Okay. So again, when your primary energy voltage is equal to critical voltage 1 or critical voltage 2, your total yield is 1 and you have no charging. Okay. Now, obviously that sounds great, right? But in theory, very hard to figure that out, right? And you may not have the ability to dial that into your microscope anyway, okay? You may only have a set voltage steps that you can use, but anyways, you know, in practice, it's a little hard to do this, right? To actually find that appropriate voltage to prevent that from occurring, okay? And again, also, right, we're talking about down here, I believe these are in the range up to a few keV, right? So, you know, these aren't like hundreds of keV here that we're talking about when we're looking at this. These are relatively low voltages, like the voltages you would find in an SEM. Okay, so we've kind of addressed the basic idea of charging, but then the real question is why do we care about it, right? Why is charging bad, and why do we have a problem with it? Okay, so if we look at the case where we don't have any charging, right? So let's say we have a non-conductive sample, but we apply a conductive coating to it, and that is properly grounded to whatever the sample is sitting on, which in this case is conductive carbon tape. Okay, so all of those electrons that are shot at the sample, right, they now have a way to effectively wander out of the sample and make it to ground. Okay, so we don't end up with a charging issue here. Okay, but let's say instead that we don't have a conductive coating. Okay, if we don't have a conductive coating, then we end up with an accumulation of charge near the surface, and my electrons in my beam are, of course, themselves charged, right? So what happens is you get Coulombic interactions between the beam and the sample, okay? And this is not good because this will change the trajectory of your electrons, it will deflect them, it will introduce changes in the beam shape, okay? And so this is a problem, okay? So you get this unwanted Coulombic interaction with the incident beam, and it causes unwanted distortions and deflections to the beam. And we see features in the SEM images that we really don't want there, that they're not very good aesthetically pleasing, they're not true to what the sample actually is, and they're just, you know, they're just unwanted and something that we don't like having to deal with, okay? So yeah, coating's there. Okay, so if you look on the left here, in the case of an as prepared sample that doesn't have any conductive coating, okay? So the circles, I should say, not the circles, the ellipses indicated in red, okay, are where we have what are called scan excursions to the beam, okay? So you can see in this case, because the fast scan direction is from left to right as the beam is moving from top to bottom through the image. So we see these things in a charge sample called scan excursions, which is basically a disruption to the scanning sequence, okay? And obviously this isn't good, right? Because you see these streaks all over your picture and it makes it hard to see the actual, you know, sample itself, okay? You also see parts where you have you can have a supersaturation of signal or signal clipping, like what we see up here in the upper left corner, okay? So this is another hallmark of charging, is where you have a difficulty with getting proper optimization of your detector, because you're usually dealing with some areas that they get super saturated with the signal, and it's hard to, adjust your gain and your brightness and contrast, I should say, to get rid of those, okay? But if we look what happens when we add a coating, right, all of this goes away. And actually we can see also, right, in the uncoated sample, it looks kind of flat, right? But if we look at the sample with the coating, we see additional depth perception that we don't see or weren't seeing with the sample on the left, right? And this is actually the exact same area that we were seeing on the left, right? So you can see the left sample actually looks kind of flat, and the one on the right, once we apply the coating, allows us to see the actual morphology far more accurately, okay? So again, this is an example of why charging is not good and how it can affect, right, what we're seeing and the results that we're seeing, and trying to get an accurate picture of the sample, okay? So, right, so we note the scan excursions in the fast left to right scan direction. We note that we have areas with signal saturation, which is the same thing as clipping, okay? And we notice that once we add the conductive coating, we see far superior detail, and we don't see any artifacts either, right? We don't see the scan excursions, we don't see the signal clipping either, okay? Here's another example of this. So same idea. On the left, you have an as prepared specimen, right? And you see the same things. So we see a lot of signal clipping, right? Saturation of signal. And then we apply the conductive coating and it goes away, right? Goes away. And we can see much better detail in the image as well, right? So in the areas where you have all this saturation of signal, it becomes really hard to actually pick out what's there, okay? But when you have a coating on there, conductive coating on there to bleed off the accumulated charge, you no longer have this issue, and you can actually see the structure how it really is, okay? So, and that's even with a really good detector, right? So most detectors now in the SEMs, they are 16-bit dynamic range, which is really good, but it can still become very challenging and nearly impossible to optimize the detector so you're not seeing this saturation, again, when you are dealing with this charging issue, okay? Okay, and then if you have a really bad issue with charging, you can end up with what's called an electron mirror. Okay, so literally your sample accumulates so much charge that your electrons deflect right off of it and never actually make it to the sample, and they end up imaging the inside of the microscope chamber itself. Okay, so what you're actually seeing here, this is actually the BSE detector that's right under the pole piece right here. Okay, and then this is the surrounding area of the chamber, okay? So yeah, this is the worst case scenario, right? This would be like something like if you were imaging like a piece of glass, for instance, right? An uncoated piece of glass. That would be a perfect example of what could happen, okay? Okay, so now we've been discussing this in reference to SEM, okay? We want to now ask the question about STEM though, okay? So now at the beginning, I asked you the question about, well, do you fundamentally understand how STEM works, okay? So the fundamental way that STEM works is you put a beam or a probe, right? If we're talking about, STEM, right? We have a focused probe, or if we're in TEM, we have a broad beam, okay? We put those onto a sample, and the sample is very thin so that the beam can transmit through it, okay? So there is your answer, right? You have a sample that is so thin that the electrons transmit through it, okay? In other words, they never accumulate inside of the sample, okay? And this is just a the rest of this here, right? The important part was this, okay? Right, but you can see, right, my beam is transmitting through, right? In this case, I get a seabed pattern, right? I have an annular detector, I'm detecting incoherent scattering, okay? So then again, right, what is the fundamental operating principle for all of STEM? It is you take a beam of electrons and you transmit the beam through a very thin sample, okay? That is the fundamental operating principle for anything that we deal with in STEM. Okay, doesn't matter, right? It all comes down to that, right? Literally, it's so interesting, right? How complicated STEM is, and yet you can boil it down to its essence in just a sentence like that. You're taking a beam of electrons and transmitting them through a sample that is very thin. Okay. Okay. So charging is therefore not an issue. Okay. It can't be an issue physically. It can't. Okay, if your electrons are simply passing through the material and they never accumulate, how could you ever get charging? And the answer is you can't, right? You can't. I have imaged and worked on some of the most insulating materials you could possibly think of, and I have never come across a charging problem once, okay, as far as working on them doing STEM work, okay? Here's a great example, sapphire, alumina, okay, along 0 to 2 bar 1 zone axis. I showed, I think, at least a snippet of this image in my MSA webinar, okay? But sapphire is unbelievably electrically insulating, okay? And it also has a really, really high optical band gap as well, okay? Which is, of course, expected for something that is very electrically insulated. I don't remember what the band gap is. I want to say it's something like 6 or 7 electron volts, okay? But this is a very insulating material, okay? And yet, with properly prepared samples, of course, people take beautiful STEM images of sapphire all the time, okay? So here's your first proof, right, that no charging occurred and there was no conductive coating put on this sample, right? You never want to do that in STEM, right? You wouldn't want to put a coating on it because you would be obscuring the detail then. It's the same idea behind like how we don't want damage layers on the surfaces, or we want to be careful with support films behind particles because those cause a distortion. It would be the same thing if we applied a conductive coating, right? That would degrade the image quality. The good news is that we don't have to do it, right? We don't have to do it because the electrons don't accumulate. They just transmit right through, okay? Here's example 2, okay? Another very insulating material, an oxide, boron suboxide, okay? Also taken along the same zone axis as what I showed you for the sapphire, okay? Has a similar kind of crystal structure, but again, also is very, very electrically insulating, okay? Not quite as bad as the sapphire, but that's still really, really insulating as well, okay? This is not a conductive material at all. This is a pure insulator, bar none, end of story. And yet we can take really nice STEM images of it, okay? This, of course, being just a high-res image. Okay, but this is not just related to high-res like I showed you in the previous 2 slides. So here is head of stem of 4H silicon carbide along 112 bar 0. Okay, this was not taken with CS correction, so this was taken on the Talos. This was an uncorrected image, and still a very nice one as far as coming from an uncorrected microscope, because we're resolving those silicon columns very readily here, of course, right? And silicon carbide, again, is a very insulating material with a very high band gap of around 3.26 electron volts, okay? So even here, right, no problems, okay? So again, it's not an issue, with STEM either, or TEM, okay? The issue doesn't matter as long as, right, you're transmitting through the sample, okay? Again, very insulating material. We can take great images of it. No issues with charging, everything's fine. Right, and then the last example, strontium titanate. Again, very high band gap insulator, right? Again, very and highly electrically insulating. And this is probably the most studied and imaged material by HADF-STEM ever, okay, is probably strontium titanate as viewed upon the 001 zone axis. You will probably find more HADF-STEM images of this particular material along this zone axis than any other sample. Possibly even silicon along 110. But I haven't done a complete survey of that, okay? But we regularly take these on our Themis, right? We don't apply conductive coatings, we put them right in there and it's good to go and it works perfectly fine, okay? So we have all the evidence in addition to the theoretical basis to back up the claim that we don't have to worry about charging when we're doing STEM work, okay? All right, so just to summarize, do we have to worry about charging in STEM? Nope, we do not. Okay, we do not have to worry about this. Okay, but just to go back, right, and the reason is we get charging because of electrons accumulating. Okay, right, electrons have to accumulate. Okay, and we saw how in the case of samples usually used in SEM, right, how these can be detrimental. We get artifacts and we get a degradation in the image quality. And this can happen in SEM, not just in insulating samples, but any samples that do not have proper grounding as well. So in other words, if you had a metal sample that you were imaging, but it was electrically insulated from ground, you would have charging issues with that as well. Okay, so it's not just an issue for so charging can affect literally any sample in SEM. Again, if you don't have proper grounding and you don't have proper and if necessary, you don't have a conductive coating applied. Okay, so assuming you have the grounding issue resolved, right? Applying the conductive coating is the last thing to do to get rid of the charging effects. Okay, now I will say, because some of you probably already know this, applying a conductive coating is not the only way to address charging in SEM. Okay, there are things we can do as far as the actual scanning that we do in the SEM to reduce the charging, which is a video I hope to do at some point, because it is pretty cool to see how this can work, or at least improve the quality of your images. And there's also things like variable pressure or environmental SEM, which are used also as ways to help mitigate the charging. And again, at some point, I hope to possibly address those. But for the time being, we're only considering standard high vacuum SEM, and you're putting a conductive coating on there, okay? And we're not doing anything crazy with the way we change the SEM scanning, okay? Although again, right, at some point I would like to address those other ways to potentially deal with charging, okay? But as far as STEM is concerned, it is really of zero practical concern, right? Because the electrons in the beam, they transmit right through the sample, okay? And if that is happening, okay, you can't get accumulation, right? The only time this may become relevant is if you have a sample that's really, really thick. But if your sample is really, really thick, you've got other problems, okay? Not just the issue of charging, but just that you're not going to be able to see anything useful, period, right, if your sample is very thick, okay? And as I showed you, right, there's lots of high quality STEM data that are being obtained and have been obtained for decades now from very, very insulating materials. Okay, and I gave you 4 examples here, just to drive the point home. So that's the video I wanted to do on charging. So please like, subscribe, and share. And I look forward to putting out some more videos here very shortly. All right, thank you, everybody.